Okay, good afternoon, everyone. Today we're going to continue our discussion on factorial designs, and we're going to continue on our example on the battery life, where we stopped at comparing the different material types in terms of their effect to battery life. Okay, so here, if you remember, we tried to use Tukey's test to determine whether there is a significant difference between the different material types in terms of their effect on battery life. Okay, and as you can see here, okay, before we go to that discussion, I remember that we had to take into consideration the fact that there is interaction between material type and temperature. Therefore, to go around this, we had to set temperature at a certain level. In our case, we set it at 70 degrees Fahrenheit, and then we compare the material test using that level. Okay, and as you can see here, y bar 1, 2 dot is equal to 57.25. Y bar 2, 2 dot is equal to 119.75. And y bar 3, 2 dot is equal to 145.75. So these are basically the mean observations per material type at the temperature level of 70 degree Fahrenheit. Okay, and to get our T parameter, as we mentioned last time, T at 0.05 is equal to Q at 0.05 with parameters 3 and 27, and multiplied by square root of MSE over N. Okay, and Q of 0.05 with parameters 3 and 27 is equal to 3.5. Multiply this by your MSE, which is 675.21 over the number of replicates N, which is equal to 4. And we get T of 0.05 equal to 45.47. Now we compare the difference of the estimates for the material type to this value. Okay, for 3 versus 1, we get 145.75, the mean for material 3, minus 57.25 for material 1, and that is 88.5. We do the same for 3 versus 2 and 2 versus 1. For 3 versus 1, 88.5 is obviously greater than T at 0.05, which is equal to 45.47. Therefore, based on this comparison, we can conclude that there is a significant difference between material 3 and material type 1. Looking at the numbers for the comparison between the other material types, we can see that 2 versus 1 is also significant, 62.5 being greater than T at 0.05, whereas 3 versus 2 is not. Okay, so here we can say that 3 material types 3 and 2, okay, are actually better, okay, in terms of their effect on battery life than material type 1. Additionally, however, we can also say that 3 versus 2 is not significant. Therefore, material types 3 and 2 do not have a significant difference in terms of their effect on battery life. Okay, so now we move on to estimating the model source of variation. Okay, so here we know that SS model, or sum of squares of the model, is equal to SS material plus SS temperature plus SS interaction. And we have already previously computed these terms, okay? And these are the values for these 3 terms, okay? We add them all up, we get 59,416.22. So this is SS model. To get R squared, okay, the model source of variation, we just get the ratio of SS model and SS total. Okay, so we know that SS total is 77,646.97. And so the ratio of SS model versus SS total is just 0.7652. This means that about 77% or 76.52% to be precise, okay? 76.52% of the variation in battery life is explained by the model, consisting of your independent variables, material type, temperature, and their interaction. This also means that at least one of these three terms in the model is significant. Okay. And so if we investigate further, this is a computer output using Design Expert, and as I've mentioned previously, you can of course use other statistical softwares to come up with basically the same output, assuming that you use the software correctly. Okay, so as you can see here, okay, this is the ANOVA for the Factorial design corresponding to the battery design experiment. And you can see here the sources of variation in the first column, and then the sum of squares, the degree of freedom, the mean square, the F value, and the corresponding P value. All right. So as you can see here, material type, temperature, as well as their interaction are all significant because of p-value that are very low, much lower than 0.05. And then as we have already discussed, the F values are higher than the corresponding test statistic for each of these terms. Okay, and here below you can see the residuals here, and here you can see also the R squared as well as the adjusted R squared. Okay, so the R squared, as we have computed, is 0.7652. The adjusted R squared is adjusted for the number of terms that is included in the model, because the R squared can be artificially increased by adding more factors in the model, and the adjusted R squared takes this into account. So as you can see, the number is slightly lower than the R squared, the computed R squared, but still is I think relatively high, okay, in terms of the ability of the model to explain the variation in the battery life. Okay, which means that again, at least one of the three terms that we have identified is significant. Okay, next you can also see here a JMP computer output, and there is a plot here that shows you the battery life, okay, the observed battery life versus the predicted battery life, okay, predicted using the model. Okay, and with this, your R squared is also 77%, as we have computed, around 77%. Okay, and you can see the familiar numbers over here. Okay, and here is the residual plot, okay, by the residuals by the predicted values. Okay, and we don't see any significant patterns, therefore it is reasonable to assume or conclude that the model is adequate. Okay. And we touch on this again to remind you that model adequacy checking is very important. Okay, so And we know that the primary diagnostic tool is residual analysis. And recall that residual E sub ijk is equal to your observation Y sub ijk minus Y hot ijk. Okay, and Y hot ijk is uh, also equal to your Y bar ij dot. Okay, and these are basically the computed residuals for our battery design example. All right. And okay, so let's just go back to that just to make sure that we are all on the same page. Y ij dot is basically the mean, okay, for cell ij. Okay, so if you recall, we already, if you go back to the given data for this example, you have 4 observations per combination of material type and temperature, okay, because we have 4 replicates. And you just get the mean of those observations, okay? So that's your Y bar ij dot. And then you just subtract that from the observed value to get your residual. And now plotting the residual in our normal probability plot and plotting the residual versus the predicted value, you can see again that the normality assumption is satisfied given that our residuals are very close to the normal line. And then we don't see any significant pattern here. So we can conclude that the model is adequate. Okay, so we can say the same for residual versus material type and residual versus temperature. We don't see any significant pattern. Therefore, we can say that the model is adequate.
Okay, so let us now move on to estimating model parameters. Recall that the effects model is expressed in this equation. The parameters in this model can be estimated using the least squares. Now, since there are 1 plus A plus B plus AB parameters to be estimated, then there are 1 plus A plus B plus AB normal equations. Now, using the method discussed by Montgomery in chapter 3.9, it can be shown that the normal equations are as follows. So you can see indicated on the left, to the left of the equation, the different parameters to be estimated. So this one is for mu, for tau I, and then you have beta j, and then tau beta ij for the interactions. Now, since the effects model is over-parameterized, there are A plus B plus 1 linear dependencies. And so, to obtain unique solutions, the following constraints are imposed. Okay. Now, applying these constraints, the normal equations become significantly simpler, and we get the following solutions. For mu hat, this is equal to the grand average. Okay, the fitted tau i's or tau I hat is equal to the row average minus the grand average. For beta j hat or the fitted betas, this is equal to the column average minus the grand average. And then for the interaction parameters, tau beta ij, okay, this is equal to the cell average minus the row average minus the column average plus the grand average. Therefore, the fitted value yijk is equal to the average cell of ij, actually. So we basically substituted the derived expressions for these parameters, these fitted parameters, which are these things here. And we get that the fitted parameter yijk is just equal to actually the cell average at combination ij.
Okay, now let's move on to the choice of sample size. The operating characteristic curve or the OC curve can help in determining sample size. And you can find this in Appendix Chart 5 of Montgomery. Now, this table shows the appropriate value for phi squared as well as the degrees of freedom for the numerator and the denominator. Now, as suggested by Montgomery, the most effective way of using the OC curve in chart 5 of the appendix is to find the smallest value of phi corresponding to a specified difference between any two treatment means. Okay? And this one is if you are given or you assume a difference for the rows, this one is for the columns, and this one is for difference between interaction means. Now, suppose that before performing the experiment, the battery experiment that we've been using, you decide that the null hypothesis should be rejected with high probability if the difference in battery life between any two temperatures is 40 hours. Now, assuming that the standard deviation in battery life is 25 hours, then we can use this equation to derive the minimum value of phi squared. Recall that this one, okay, is to be used if we are looking at column treatment differences, average differences. So that's why we're using this. And by substituting the values, we get the expression that can help us identify the minimum value of phi squared. So it's 1.28n. Now, assuming significance level of 0.05, we can use Appendix Table 5 from Design and Analysis of Experiments by Montgomery to arrive at the following. Okay. You can see that at n equals 4, the risk beta is equal to 0.06. Now, this means that the power of the test is about 94%. That means that there is a 94% chance of rejecting the null hypothesis if the difference in the battery life at any two temperature levels is greater or equal to 40 hours. Now, based on this, we conclude that 4 replicates is sufficient as long as the assumption that the standard deviation of 25 hours is not seriously erroneous. Now, as suggested also by Montgomery, you can repeat the same procedure at different values of standard deviation to see how the values of n change with respect to changes in the assumed standard deviation. Now let us proceed to the assumption of no interaction in two-factor factorial designs. Now, there are instances when it is reasonable to assume that there are no factor interactions. The effects model can therefore be simplified and expressed as follows. Y sub ijk is equal to mu plus tau I plus beta j plus epsilon ijk for all I equals 1 to A, j equals 1 to B, k equals 1 to n. Of course, the simplified version lacks the interaction term. Now, as a caveat though, the assumption of no interaction should be used with care because the presence of significant interaction can have a substantial effect on the interpretation of data. This is the ANOVA results for battery life data or battery life example, assuming no interaction. Now, the critical value of F at 5% level of significance with degrees of freedom 2 and 31, okay, here 2 and 31, for both material types and temperature, okay, is 3.305. Now, as in the full model, in this model, we can see that both factors, material types and temperature, are significant, given that your F naught is greater than the critical value of F. Our F naughts here are 5.95 and 21.78, which are greater than 3.305. Now to get the value of y hat ijk, this is equal to the average at row I plus the average at column J minus the grand average. So again, we don't have the term corresponding to the interaction. Okay, and if we plot the difference between the fitted value, okay, yijk, or if we plot the cell average, okay, the difference between the cell average and the fitted value ijk, okay, versus the fitted value ijk, we can see that there is a pattern. So it goes from positive to positive again, and then negative. And this signifies that the model is actually not adequate in explaining the variation in the battery life. And we know that this inadequacy is because of the removal of the interaction term. Now we move on to one observation per cell, okay, for the two-factor factorial design. Okay, so for one observation per cell, for at least for the two-factor factorial design, the effects model becomes like this. The effects model can be expressed as such. Once y sub ij is equal to mu plus tau I plus beta j plus tau beta ij plus epsilon ij for I equals 1 to a and j equals 1 to n. Now, this is the corresponding ANOVA table for the two-factor model with one observation per cell. And looking at the expected mean squares, you will see that the variance is not estimable because it is not obvious how one can separate the two-factor interaction effect and the experimental error. Now, with this, no test on the mean effects can be done. And this can only be done if the interaction effect is zero, and that is tau beta ij is zero for all I and j. If the interaction is not significant, then the model becomes like this. Okay, so you can see that tau beta ij is not in the equation anymore. If this model is appropriate, then the residual mean square is an unbiased estimator of the variance. Now, the main effects can be tested by comparing the MSA by MS residual and MSB by the MS residual. To test whether the interaction is present, we can use the procedure developed by Tukey in 1949 as described in the Design and Analysis of Experiments by Montgomery. Now, SSN, or the sum of squares for non-additivity, is computed as such. Okay? It looks a little bit daunting, but you already know how to compute for each of these terms. All right, and some of them are given. And then your SS error is now equal to your SS residual minus SSN. Okay? And to compute for F naught, you just get the ratio between SSN and SS error divided by quantity A minus 1 times B minus 1 minus 1. Okay? So if your F naught is greater than the critical value for F, okay, at significance level of alpha and degrees of freedom 1 and A minus 1 times B minus 1 minus 1, okay, then the hypothesis of no interaction must be rejected. So let's take this impurity in a chemical product example to illustrate what we just discussed. Okay? Suppose that the impurity in a chemical product is affected by two factors, namely pressure, and temperature. The data from a single replicate of a factorial experiment are shown here, which was from Montgomery as well. Okay, so you have your temperature for the rows and then your pressure along the columns. And as you can see, there's one observation per cell, which means we only have one replicate. Okay. We already have here the computed row totals, column totals, and the grand total. To compute for the sum of squares, we use familiar equations. Okay, and so we get SSA equals 23.33, SSB equals 11.6, SST equals 36.93. And the SS residual, which is just equal to the sum of squares total minus sum of square for A minus sum of square for B, is equal to 2. All right. And so to get for the sum of square for non-additivity, we use the equation I just showed you before, which is basically this one. And we get that SS sub n is equal to 0.0985. Okay. And therefore, SS error is just equal to SS residual minus SSN, and that would be 1.9015. Okay, summarizing the analysis of variance, we get here the source of variation, the sum of squares, the degrees of freedom, the mean square, and the F naught. And as you can see, based on and the p-value, and as if we base our conclusions on the p-value, we can see that temperature and pressure are significant and non-additivity is not significant, which means that the interaction is not significant. And now we move on to the general factorial design.
At this point, take a break and we will continue our discussion in the next video.